Hello, good afternoon. Sorry. So it's a pleasure for me to introduce our speaker today. Our speaker today is Svetlana Gurevich from the, I think it's Wilhelm's, whatever. It's a very difficult name. So Svetlana was a native from, and she has insisted at this point, from Leningrad, although now it's called St. Petersburg. So after hard work, Leningrad is printing her passport. And then she studied mathematics, applied mathematics in St. Petersburg, Leningrad, and then went to for her PhD to Münster already to work with someone that is quite well known for some people here. This the now retired professor Hans-Georg Purwins. So in gas discharge problem, but from the theory side, of course. Then after concluding the PhD, then she joined the group of Professor Rudolf Friedrichs, already in Münster, working on a variety of problems with pattern formation and also nanosystems and so on, but also with some some work on localized structures. And well, very much unfortunately, the Professor Friedrichs passed away last August, so in a way, now she's headless in Münster. And just to finish, much of the work in her center now goes in a binational cooperation project with China, related also with nano problems and so on. So today she will speak about the instabilities of localized structures and dissipative systems with delayed feedback.
Thank you very much. Thank you very much for this invitation. It's a pleasure for me to be here, and thank you for the opportunity to present our results to you. And okay, they are in some sense okay without any head, but on the other hand, life goes further, and we try to keep our activities at least in some directions, in one direction. It's what I would like to tell you today. So I would like to speak about instabilities of localized structures induced by the wave feedback. And let me start from the introduction. And actually, localized structures are really common self-organized phenomena that can be found in a number of different systems, both in nature and labo experiments. And here you can see different examples of the system.
Sorry, this is needed for the recording.
I can proceed further without. Okay, and the first example that you can see here is a localized agitation pattern observed in the Gurevich research. The second example is two-dimensional so-called ferrosolitons on the surface of magnetic fluids. It's probably a known example for some of you. It's optical solitons in alkalimeter vapor. This one is a circular spreading depolarization wave in a chicken retina, so it's an example from neurophysics. Here you can see clay oscillons, so propagating oscillons in colloidal suspension, and the last example comes from experimental group of Professor Purwins, so it's a plasma sprouting gas discharge system. And you see actually that the nature of all of these structures is really different. However, sometimes properties are really common or almost the same. And of course, if you are speaking on localized structures like that, sometimes you need a kind of efficient control to do something with the system. And of course, you can imagine that probably for ecologists working on some erosion problem, it's necessary to have a kind of efficient control on structures like that. So typically it's extended structures like labyrinths or stripes of vegetation, but of course there are some localized spots as well. Of course, in nonlinear optics, it is important to control a structure if you say, okay, they are really important for optical information processing units and so on. And for neurophysics, of course, such kind of spreading polarization wave is important to prevent migraine attack or even stroke. So it's depending on the application, sometimes you need some control. And of course, there are a lot of control techniques that can be applied to a standard system like this. And one particular technique I would like to discuss today, it's a so-called time-delayed feedback control, also known as Piratov control or auto-synchronization. So I suppose last year it was the 20th birthday, so to say, of this technique. And actually the idea is rather simple. So what you have here, imagine you have a general dynamical system, you have just a time evolution of some variable, which is described by some typical nonlinear function. And you have some input signal in your system described with this variable x from t, and you have some output, g from x from t, and you can construct a control force from the difference of the signal on the present state of a given system to its delay. So it's, you can see it here, you just construct, you give your signal to the time t, divided from the signal to the time t minus tau, to its delay time. And after that, of course, you can, if you're interested to a particular control, which component of the system is connected to which one, you can do it with a kind of coupling matrix if you're interested in, and you put your signal into the system. That means that the control force would be like that, and the controlled system, this one, would be like this. So you just add this feedback delay term, and that's all. And of course, all the information about coupling is in this coupling matrix. Okay, now, advantages of this approach is, of course, the first one, that the proper choice of tau, the control force vanishes if such kind of state, what you need to stabilize, is reached. That means that this control is in some sense non-invasive. So if you reach the state that you would like to stabilize, you have any control anymore, and you have the same system as before. Typically, only minimum knowledge of a system is required to apply this method. If you have to stabilize a kind of periodic orbit embedded in some chaotic attractor, you need to know just the frequency of this orbit, and that's all. And typically, it's rather easy for experimenters to implement control like that. And of course, if you have some advantages, you should have a big disadvantage to keep an equilibrium. And a big disadvantage means that, of course, if you introduce a time-delayed feedback, we have to deal with delay differential equation. That means that if I have an extended system depending on space and time, I have infinitely many degrees of freedom, and I introduce additional infinitely many degrees of freedom due to delay. That typically makes the system much more complicated from a theoretical point of view, but of course it's interesting topic to discuss. And this scheme was applied to a number of different systems, but typically all the systems ask you should stabilize some unstable trajectories, periodic orbits embedded in some chaotic attractors, or stuff like that. You can control chaotic orbits as well, and you can apply it to low discharge, Taylor-Coed instability, and a lot of different stuff. But typically, the problem is that if you have an extended system, you have the influence of such kind of time-delayed feedback is not understood to a large extent. And that's why what we are interested in influence
the impact of delayed feedback on the dynamic of spatial incidental system. And an example that I would like to discuss comes from Nonlinear Optics. So we are speaking about localized structures that typically are referred to as cavity solitons in Nonlinear Optics. And at this point, I would like to say that depending on community you are working with, the name of the local structure also changes. So there are no common name for it. Of course, you can say in the case of dissipative system, you can refer to the structure as dissipative soliton, but some people are not happy with this definition. And for example, in chemical system, you can find nomenclature like spots or pulsars, as well as in some biological system. Plasma filaments in the gas discharge, cavity solitons in nonlinear optics, outer solitons in some Russian literature concerning the same point. So there are a lot of names. And in order to make all people happy, I just say localized structure. But depending on community, you should choose the name that you have to say in order to meet audience. And for nonlinear optics, we discussed nonlinear cavities. That means we discuss cavity solitons. And it's a kind of a toy model, a really simple model, no optical resonator field with a nonlinear media, driven coherently by external injection field, and the theoretical work of Münster and co-workers about the stuff. And you see that the delayed feedback is given by this external reflector located at a large distance from the right facet of the cavity. So you're interested in this kind of toy model. You're interested only in a distribution of a real valued order parameter, and this real valued order parameter is nothing else as deviation of the electrical field from its stationary value. This is deviation is Q. We are in 2 dimensions, so we are in transversal plane. And the equation that one can write at the onset of the optical distability is like that. You have a time evolution of deviation of the electric field. You have some spatial operators, a nonlinear function, a cubic one, and you have a time delayed feedback. So Y here is the input field, and C is the cooperative parameter if you are speaking on nonlinear optics stuff. But however, if you say, okay, let alpha be 0, so alpha, again, I forgot to say it, this term is the delayed rate, how large is the delay value, and tau, again, is delayed time. And you see that if you have just one complement, you have unity coupling connections, if you like. Okay, so now suppose we have no delay. And probably you can recognize that this equation is nothing else as a scaled variant of Swift-Hohenberg equation. So actually just Swift-Hohenberg equation. And here you have, you can see a canonical form of Swift-Hohenberg equation with a strange cubic nonlinearity without quadratic term, but it doesn't really matter in principle. And of course, if you have a classical Swift-Hohenberg equation, Swift-Hohenberg equation, as you probably know, is one of the most studied equations in nonlinear physics, and has a lot of application from nonlinear or fluid dynamics, binary mixture to nonlinear optics, as you can see. And actually, this equation has one feature or bug, depending on your point of view, and this feature means that the system is gradient. The system possesses Lyapunov functional, and that means that typically no Hopf bifurcation of non-covalent wave are possible. Each perturbation leads to the minimum of this functional, and all stationary solution, stable stationary solution, satisfied the stationary version of this equation. So the system is really boring in some sense. So you have just a stationary solution, and that's all. But of course, the thing can change if we add a time delayed feedback. Because of course, if we add a term like this, the system loses its gradient structure. And now, from now on, I just write down the same system in a general form. So again, we have a time evolution of our state vector, and it could be one component, it could be in general a lot of them. We have some nonlinear operator acting on the same state vector, and we have time-delayed feedback with unity coupling matrix. As a really simple approach, we don't need to go to really complicated coupling matrices, because the unit one, the dynamic is enough to understand it first. Okay, again, what we are interested in, we are interested in stability of stationary solution of the system, Q0 or Q0. That means that the stationary solution satisfies this equation. And in a simple form, it's a single localized structure with rotational symmetry. Of course, in Swift-Hohenberg equation, a lot of localized structures can be found, kind of localized rings, localized hexagons, localized stripe patches, but we are interested in a really, really simple solution. It could be in the form of bright soliton or dark soliton, depending on the parameter you are interested in. And you see that actually, because the stationary solution is time independent, the stationary solution of the system without delay and with delay is the same. However, stability of the solution, of course, may change. And it is what we are interested in. So now, before we look at solutions with delay, probably you are not so familiar with linear stability of such kind of systems. That's why now let us suppose that we have no delay, the delay rate is 0, and we are interested in linear stability. That means that we introduce a small perturbation of the stationary solution. We can write down an equation for the perturbation, and of course, for the first glance, we are interested in linear eigenvalue problem. So here, mu are eigenvalues, and phi are eigenfunctions. And the first point to notice is that if the system teaches translational invariance to respect to the spatial coordinate, mu equals 0 is always a solution, so we have to deal with the neutral stability. And the corresponding eigenfunction is often referred to as Boltzmann mode, and it is nothing else as a derivative of a stationary solution with respect to spatial coordinates. And of course, the existence of this neutral mode doesn't disturb the stability of your system. You have a neutral stability. That means if you add a small perturbation in the form of the Boltzmann mode, your solution will be shifted to a different spatial position, and stability is not affected, of course. And of course, apart from this neutral mode, you have some modes of the discrete spectrum. And here you can see the first three modes of the discrete spectrum. The n equals 0 mode corresponds to the change of the size of the soliton, so it's called breathing mode. The first one is just a Gaussian mode, corresponds to the shift, and you have two of them, to the x and to the y direction. And n equals 2 corresponds to the deformation like this or like that. We have two of them. And the typical spectral situation is like this. So nothing happens. All modes are stable, and the rest of the modes, or continuous mode spectrum, is somewhere here. Okay, it's a situation what we have. And now, let's look what happens if we add a time-delayed feedback to a system. So let alpha be not 0. We consider the whole system. Of course, we can perform the same stability analysis. We can calculate a linear eigenvalue problem. And now, because of the choice of this coupling matrix, you see that the coupling matrix commutes with linearized operator, with L prime. And that means that the spectra of delayed and undelayed problem are the same, but eigenvalues are of course different. And that means that we can recognize our old eigenvalue problem from the left-hand left-hand side without any delay. And we can write down a transcendental equation connecting spectra without any delay of the left-hand side and with delay on the right-hand side. So you see this transcendental equation, and it's not so nice to deal with. However, it's possible to solve this equation. But first of all, one point to mention, again, all mu's are real. Lambdas can be complex, of course. And the second point, each value of mu generates infinitely many values of lambda because of delay. And now if you're interested just in the solution of the system, you can solve it with a so-called Lambert BW function. This function is defined like that. But of course, it's nice. You can solve it analytically, numerically, of course. But probably it would be interesting to look at some special cases. And interesting special case is, of course, what happens with a neutral stable mode with 0. And you see, if mu is equal to 0, this equation becomes easier in the sense that you see immediately that lambda equals 0 is also a solution. What means that neutral mode becomes remains, so to say, 0 remains 0. But of course, you can see that you have another solution of this equation, and if you can approximate this solution, it's look like that, and you see the sign of the second eigenvalue strongly depends on the value of the product between delay rate and delay time. And you see that if this product is smaller than 1, this red mode is stable, and after that it's approaching to 0, makes 0 exactly in alpha tau equals 1, and goes through. And typically it is what happens if in a system a neutral mode becomes in some sense unstable, a soliton starts to travel with a constant velocity. And here you have the same situation, only differences that both eigenvalues correspond to one neutral eigenfunction. You have no additional instability. All the instability is induced by a neutral mode.
The other modes don't move to the right when you are.
They move.
And they cross the axis?
Yes, you can see it in the next slide. Now we introduce a new control parameter, and a new control parameter is a product of delay time and delay rate. And now let's look what happens with other modes. And all critical modes becomes unstable if a value of this new control parameter is larger than a maximum between 1 and 1 is the onset of the strip, induced strip bifurcation, and this value. So in principle, you have here just the eigenvalue to 2 in some sense. And now the next point is that, of course, you can write down a kind of solvability condition now for each mode, that each mode becomes unstable. As the first point, the solvability condition is like that. And the second point is that because the value of mu is really close to 0, typically the maximum is at 1. That means that 1 becomes a bifurcation point of really high codimension. Okay, and now if you solve this solvability condition, you can calculate a kind of phase diagram or bifurcation diagram. So here you have a product of delay rate and delay time. Here you have delay time. And R equals 1 corresponds to the onset of spontaneous motion. Probably it's complicated to see what's 10 here. So it's a threshold for spontaneous motion. And now, if you fix the value of A, like here, and go in this direction, in this area, all discrete modes are unstable. You have a traveling soliton, and you have a breathing, and you have a change of the shape. Here, the change of the shape is stable, you have traveling and breathing, and here you have only traveling. So, and now, okay, it's a nice phase diagram. The only one problem is that, of course, if a presence of time-delayed feedback can influence the stability of stationary solution, of course, the stability of homogeneous steady state can be influenced as well. So the analysis is not complete. So we can say, look what happens with a homogeneous steady state. And of course, basically, if you just take a normal perturbation to the uniform solution, you get the same transcendental equation depending on the k number or the wave number k. And now let me just show what happens. What we have done, we have plot eigenvalues lambda from k for different values of delay time for fixed a. And if you have no delay, you have a stable situation, and you have just a half of the growth rate, real part of nu. And now, if we add some delay, the homogeneous steady state becomes unstable, and you see that k equals 0 is the dynamics. That means that you have a kind of traveling wave bifurcation with k equals 0. Sometimes people say it should be a homogeneous hop, but in principle it's a traveling wave with k equals 0. Now, if you increase your delay time, the k equals 0 becomes negative, and you have, in this situation, a really narrow band of unstable modes. So you have just a classical traveling wave bifurcation. And further increasing in tau leads to the stabilization of the solution. That means that this dynamics could happen only for small delay times. And an interesting point is that decay rates for a large k, it's not large, but you can imagine what it looks like for large delays, for large keys, sorry. You see that this decay rate is different. Yes, because here you have decays like k to the fourth, as it should be for Swift-Hohenberg equation, and here you have decay like k squared, which is more typical for reaction frequencies. And that means that probably for this delay, some interesting dynamic could happen, and this dynamic could be not generic for Swift-Hohenberg. Okay, now we can complete this phase diagram or bifurcation diagram just to by adding corresponding branches of traveling wave bifurcation of this strange homogeneous Hopf bifurcation. And here three first branches of this Lambert W function are shown for this traveling wave bifurcation. And now let's look what happens in direct numerical simulation. So what we are doing now, we just fix the A about 1 and go in this direction. Okay, so now let me show video what happens. So I have to stop it and can stop it. Okay, so probably you can see it. Okay, what happens here? I'm starting with a bright soliton in the region where this homogeneous Hopf bifurcation happens. So we have oscillating homogeneous state. The soliton breaks down to the dark soliton. The homogeneous steady state goes to some mu value, and this value is just a solution of the delayed equation. And after that, the soliton, however, seems to survive and oscillate a little bit on the oscillatory background. So we have oscillating soliton on oscillatory background, and in principle it's nothing else as a transition from a bright soliton to a dark oscillon. And here you can see an example of oscillon in vertically vibrated granular media. So the system is different. And I don't know probably I start this video. You cannot see it well, but in principle you can recognize it. You have oscillatory background and you have oscillating soliton on this background. Okay. Now let's go.
But it shows always dark soliton.
Yes. It was a bright soliton, but of course, in order to get a bright oscillon, I have to start with a dark soliton. So you have just a inversion. Now, in this region, homogeneous Hopf is stable, and we have just a traveling wave, a normal traveling wave. So a bright soliton becomes unstable, and a kind of soliton ring is growing. It's not so interesting. And further increasing of tau leads to really interesting dynamics. And now, in all these simulations, homogeneous steady state is stable. That means that all instability are caused only by discrete modes of the soliton itself. And I'm starting with this simulation. So you see, the solitons tries to oscillate a little bit, have to move, and the mode, the change of the shape is unstable. This mode is unstable, this n equals 0. And at the end, of course, if the shape is changed, the curvature instability impacts on the dynamic, and you have transition to a complicated labyrinth pattern, like that. Okay, I have a periodic boundary condition, that's why it's a kind of artifact of the simulation. And at this point, I would like to say that, okay, labyrinth pattern is, in my opinion, not really a generic solution of the Swift-Hohenberg equation. And if you remember this plot with this black curve, it's exactly the same parameter. So it's in parameter regime where you can find this labyrinth pattern. This growth rate behaves like growth rate in reaction diffusion system, where labyrinth pattern is really common solution. Okay. The further increasing in tau leads to the fact that the change of the shape becomes slower, and that means that on the same time scale, no labyrinth pattern, but a kind of wave segment appears. And now let me show this simulation. Here we are in the region where all discrete modes are stable, but we have some relaxation behavior, so to say. They are stable, but of course they can influence the dynamics at the beginning of the simulation. And you see what happens. The soliton oscillates a little bit, tries to move. The shape is changing. However, soliton says, okay, actually I'm stable. I'm stable. Yes, I'm stable. And now he just go further with a constant velocity. And interesting thing is, you see that actually the soliton remains almost radial symmetric. You have no pronounced change of the shape in the simulation. It's actually an interesting point because you have a drift instability. Drift instability is always connected to the symmetry breaking, so you have to have a kind of change of the shape. But in this case, it's really not pronounced because of the rule. And further increasing leads to just a boring drifting with a constant velocity, nothing happens. And now, before we are going to bifurcation analysis, let me discuss this labyrinth pattern. And I have said that this Ferragas control is really good stuff because they have a kind of non-invasive control. But of course, I have non-invasive control if I try to stabilize unstable solution. Here, the situation is completely different. I try to destabilize a stable solution. I cannot reach a kind of state that I would like to control. That means that in this case, I have no non-invasive control in some sense. I have just a forcing. I just force my system with this delayed feedback. And in order to illustrate this point, I have just started the simulation like this. And after a labyrinth pattern is formed, I just switch a control down, off, and you see that the system tries to go back. Okay, here the problem is that this labyrinth pattern was complex, and the complex structure is not simple connected in some sense, and that's why this end state would be not one soliton but a set of localized structures. But if you just accelerate it a little bit, at the end you have just a boring set of staying localized structure. You didn't reach any new dynamical state. You have just forced your system, and if you're forcing the switch off, you go back. It's just one point to emphasize. And now, let me discuss the next point. Okay, it's a really nice results, in my opinion, at least. But it's a kind of direct numerics with a little bit linear stability analysis. The question is, could we understand this kind of bifurcation with bifurcation study? Could we write down a kind of order parameter equation? Could we write down a kind of normal form of this bifurcation? And it is the next point that I would like to discuss really quickly, as I see. And suppose that we are, okay, probably not here, it's too far away from bifurcation point, but probably there. So we are in the region where only drift could happen, but however, we could say, okay, we are interested also in some relaxation behavior of these discrete modes. Here you have, again, what we have in a spectral picture, so to say. We have an unstable neutral mode, and we have two stable discrete modes, and a stable continuous spectrum. That's what we have. What we need? We need one equation for the position of the localized structure, and so to say unstable modes, and we need an equation for the shape deformation, and an equation of shape deformation for stable modes. Okay? How to do it? In order to do it, we perform the following ansatz. Again, Q naught is a stationary soliton. Stationary soliton is neutral stable. We have no additional unstable modes. We have a change of the shape, so we have a perturbation. And in this perturbation, we are just putting all of the stable modes of the spectrum. And we are multiplying the solution with a kind of shifting operator. And what does it mean? If we act with this operator onto the solution, or stationary solution, this solution would be just shifted to the position given by the state vector capital R. So in principle, you can write down this ansatz, or you can write down Q naught x minus capital R from T. So it's the same. We just shift the stationary solution. So in principle, for people who are familiar with a group theory, it's nothing else as a group orbit of the corresponding, because Gaussian mode is a generator of the corresponding Lie group, and you can write down just a group orbit. It would be like that. But without any knowledge about the symmetry story, you can just add. You can just add your position here, and you get the same result in principle. Okay, now let me just schematically show how to proceed with this ansatz. In order to get an equation for capital R, the position, we have to put this ansatz, and so on and so on and so on. And after that, we have to project. And because our problem is self-adjoint, we have to project on the same neutral Gaussian mode. It's written here. And after that, you can get the second equation for the shape deformation in a really direct way if you just extract from all your operators all terms that are looking in the direction of the Gaussian mode. So you can do it in a really formal way, and in some sense here you have no approximation. your question. Just put your answers, project, you're ready. Now, of course, you have to think a little bit on the question how to choose the form of the shape deformation, because it is necessary for the further proceeding. And here, basically what we have done, we have said, okay, we have seen that the whole relaxation dynamic is given by this discrete modes. That's why what we are doing is just a mode truncation. So we say that our shape deformation is just a sum of zero mode and second mode, and of course the second mode. And altogether, please don't afraid, it's not so complicated as it looks like. They get 3 delayed differential equations for the time evolution of the zero mode, change of the size, the second mode, change of the shape, so shape deformation, and a time evolution of the position. You see these 2 linear terms say us that both modes are stable. Of course, they have in both equations delayed term, and this delayed term are coupled with the linear part of equation for the position in such a way that here in this D it's a kind of matrix, and in this matrix exchange just the scalar products between your Goldstone mode and the corresponding discrete mode. Okay, now this equation is, or set of equations is rather complicated, and okay, it's not a normal form, of course. It's a kind of set of order parameter equations, but however, with this set of order parameter equations, you can describe a temporal evolution of your system in the vicinity of the bifurcation, if you like. That means if you're light, if you're lazy, you can just solve these equations numerically, look at the relaxation behavior, calculate the velocity, or you can consider some special cases. And of course you see that if, probably you can see it here better, the second equation is, so to say, uncoupled on the first one. So we can say that if we have used 2 equals 0, we get a really simple system like that. And for example, for this system, you can calculate the kind of growth rates of your unstable mode and compare it with direct numerical simulation. And probably, yes, here you can see on the left-hand side relaxation behavior of both 2 stable modes of the whole system, and of the right-hand side you can see instability increments in this limit, and getting with this theory and with direct numerical simulation and comparison is really good. But you can go further and say, okay, now let us suppose that all stable modes are relaxed and we have only boring drift. And in this case, you have only one order parameter equation for the position. And this equation is rather simple. You have just a cubic delay differential equation. And in principle, if you like, you can calculate your velocity from this equation directly, go to the moving frame. But, of course, some people are not happy with this equation and say, okay, it's something strange. I mean, it's a delay differential equation. And if you want to go to central manifold, you have to write down a set of ordinary differential equations where delay time would be a parameter, but not a variable. And in principle, it's possible to do. If we say, if we introduce the velocity, and of course, the velocity is slow, varying in time, and in this limit, it is possible to write down a normal form of this delayed-induced drift bifurcation. And you're probably people familiar with solitons can recognize immediately that this normal form is nothing else as a T-shock normal form of the drift, classical drift bifurcation with additional symmetry, so to say. And in principle, you see that here you have the distance to the bifurcation point, and if this control parameter A is smaller than 1, you have just one stable stationary solution, velocity equals 0. And after 1, you have 2 branches of propagation, so to say. And the interesting point, again, you see, because these stable modes were incorporated only in linear term, they have no corrections of the stable modes to the nonlinear term, and that means that to the first order, so to say, up to third order, they have no change in the shape. And that's actually what we have seen in numerical simulation. We have no pronounced change of the shape in symmetry breaking instabilities. It's a rather strange point, but in fact, it is so. Okay, and now if you are interested in propagation velocity, you can calculate it, and you see that this propagation velocity depends strongly on delay time and depends on the distance to the bifurcation point, and you can calculate it for different delay times, keeping delay rate fixed, or you can keep your delay time fixed and change delay rate, and you have a good correspondence. Okay, now if I have 2 minutes, I just, do I have? Okay. Then we discuss a little bit what happens if we add, if we consider more complicated structure like a bound state. So suppose we have no single soliton anymore, we have a bound state, we have a soliton molecule like this. It's an example. And now, in principle, of course, if you have the soliton molecule and you look at neutral stable modes, of course, you get a one mode corresponding to the shift to the x direction, one corresponding to the y direction, and of course, you get another one corresponding to the rotation. So now you have 3 neutral oscillon modes. And in addition, of course, so here you can see this Gaussian mode corresponding to the rotation. And here you get an additional mode to the spectrum, and you can see that this mode corresponds to this interaction between two. So it's this one. And of course, you have an analog to n equals 0, that changes the shape, and n equals 2, deformation like that, like that. Okay, and now in principle, we can do the same stuff as for one soliton, but for soliton molecule. And I just show a phase diagram. And you see that A equals 1 becomes the threshold for spontaneous motion and spontaneous rotation, of course. Here you see this new line, and this new line corresponds to this interaction mode. So probably, if this interaction mode are unstable, the bound state would disappear, would be unstable as well. Or probably, I didn't see it, but probably you can get something like that, if you're lucky. And the rest is the same. You have n equals 0, n equals 2. And probably the last that I show you. In principle, you can see here the same bound state of dark oscillons, if you like. You can get labyrinth pattern by self-replication. You see it becomes unstable. After that, you have curvature instability and some interaction, and you get, in this case, it's perfectly symmetric because of initial condition. But if you are waiting a little bit, you get this labyrinth, a nice labyrinth pattern. And here you see a simulation where this interaction mode is unstable. So it means that bound states becomes unstable as well. However, n equals 2 is stable again, and after that both solitons, I think, decide to become stable in the shape. It's really slow dynamic, you see it. But, okay, well done. Yes, now they have a kind of a little bit oscillation in the shape, and after that you have just a slow motion. So you have no bound state anymore, you have no pinning on another bound states, and it's really slow, but they're not state velocity is not 0. And the last simulation that I show is just a rotating and moving bound state, and you see actually that rotation is a little bit strange, so you have no rotation to the whole cycle, you have a kind of laser on. You have a kind of relaxation behavior, and after that, probably it's relaxed. You have just a motion. So here it seems to be that the dynamics, so the position of these molecules is a bint, so to say, because of delay. But in order to understand it, we have to write down another parameter equation in this for this simulation, and it's actually the point at which I can go to summary and conclusion. So let me conclude. So I hope I have convinced you that the presence of really simple delayed feedback into the system can lead to really rich interesting dynamics. That's the first point. And if we do our control or discontrol like that, you have two additional control parameters, and controlling delay rate and delay time, you actually can predict instability you are interested in. If you are interested in instabilities, because typically normal people are interested in stabilization of some unstable solution. In the case of a really simple system, if you have just a spontaneous motion with some relaxation, they are in a good position to write down a set of order parameter equation with the vicinity of the bifurcation point in order to describe the dynamics in the vicinity of this point. And you can get an analytical equation of the analytical relation to the velocity, of course. And you can see that all formulas and all theoretical stuff was done in really general form. That means that you can apply this to more complicated systems. And here I just cite a recent paper where I have generalized this stuff to the case of a non-self-adjoint operators, just to look what happens there, because there the dynamics is much more interesting, of course, in this toy model like Swift-Hohenberg. And the next interesting point is the bound state, of course. It's interesting to do this theoretical work for this solution, and in principle it's possible, I suppose, I hope so. And of course, if you are interested in some real application, for example, in nonlinear optics, you have to go probably to more realistic model. And if you go to more realistic model, you have to write down probably for the cavity field an equation for carrier density, and that means that your equation becomes complex, and probably you need to introduce a phase to your time delayed feedback. And of course, it is, I'm sure, okay, I'm not sure, I know, that a phase of this time delayed feedback can induce drift instability, at least drift instability as well. So it would be interesting to see what happens in the phase, of course. But it is all questions that could be discussed, so to say, further. And at this point, I would like to stop and to thank to Professor Friedrich, who has passed away unexpectedly for us. And of course, I would like to thank all people working in our research group for synchronization and complexity in Münster. And of course, I would like to thank you for your attention. Thank you.
Questions? It's my eyes, or there is something remaining at the end?
Yes, I suppose it's, and then you have a delayed equation, and I suppose it's just another solution remaining, and zero is oscillating a little bit. But the solution has no influence, so to say, on this soliton.
That's a solution at once, so it keeps it stable all the time?
Yes. Yes, a kind of, I suppose it's just some solution, because there is infinity many of them. This interesting story is that I see this kind of artifact only in Swift-Hohenberg. For example, injection diffusion, probably it's another parameter region and you have no coexistence or something like that.
Okay. Another one. This thing of the symmetry, I don't understand that. In the moving soliton, so you say that has no deformation?
It has a deformation. It Of course it has a deformation. This deformation is really small, it's not pronounced.
It's for the next one. It's more than that, you say?
Yes. I mean, if you write down your perturbation theory to the next order, you get this term, but in the next order, so to say. And it is different from a classical bifurcation, where you get this term in the third order as a correction. I suppose it's the difference between, because in this case, you really have two eigenvalues corresponding to one eigenfunction, to the neutron mode in the transversal space without delay space. And in a normal drift bifurcation, you have two eigenvalues corresponding to two different eigenfunctions, which becomes linearly dependent at the bifurcation point. And I suppose it's a difference. But we should discuss it later probably.
Thomas, concerning applications, during the talk you discussed the Pythagoras feedback scheme in which you have a delayed feedback term and instantaneous term. The instantaneous term may be very hard to realize. And have you had a look at what happens if your middle term only has a time delay feedback? Do you observe the same patterns? Or?
I don't.
Okay.
But it would be, of course, interesting. I mean, here the point was for us to look, first of all, to really simple system, really simple one, from theoretical point of view, in order to get intuition and feeling what could happen. And now, okay, we have this feeling, and now we can go further and to
because also you had a look at destabilization of patterns, and therefore the instantaneous term is typically stabilizing the system. Maybe you have transitions to the patterns immediately.
probably. Yes. Yes, probably.
Okay.
Have I understood your comments on the why labyrinths are not generic in this Swift-Hohenberg? I haven't got.
Are labyrinths generic?
It's my question to you. I don't. As you say, I've seen those patterns in many.
I mean,
reaction
typically.
diffusion. So, what is the difference with reaction diffusion?
I mean, typically you have in Swift-Hohenberg you have a transition to stripes with defects or to hexagons, subcritical or supercritical, but typically you have no labyrinths. You have stripes with defects. You have no, okay, if you start with a planar front and disturb it in.
It goes back to this.
Yes, in this term, yes, and in reaction diffusion system, if you start with a planar front and disturb it in transversal direction, you get to the labyrinth.
That's in the Swift-Hohenberg one. When you go to the region where the homogeneity count by
yes.
Then you got nothing.
Yes, probably, but you need. It's the question whether you need. I have only monostable system.
Yeah, exactly. But if you get close to the place where the homogeneous solution becomes, so the zero.
Yeah, of course, you need.
Zero mode may.
Yeah, of course, you need the snaking region to get localized structure, but probably it's too far away from this region. What you need.
I'm not sure. We look at it later.
I'm not sure too, but for me it was really nice to see that in this region where I have this labyrinth pattern, I have just another behavior of my growth rate. It should be something connected with it. Probably you are partially true, but I suppose that this argument is true as well, because I mean you have just another decay rate for growth for large wave vectors.
Okay.
Yes, have to discuss it.
You have shown a picture of the velocity of the soliton as a function of tau.
Yes.
That's one to the left. What is the discontinuous and the continuous?
It's not. Okay, I have forgot. I have forgot to say about it. Actually, so in principle, you can just plot this line from this formula. But of course, in this region, you have other modes that are unstable. So you have no drift, no pure drift in some sense. And that's why I have just separated two regions where you have just a normal drift without any contributions from another modes. And here, of course, this formula is not correct in some sense because you have contributions to the change of the shape and to different stories. Here you should compare not the stationary velocity, but velocity calculated from the whole model. But you can do it. I can do it.
More questions? Comments? So if not, let's thank you.